All right, so we're going to get started here on 3.1, get going more into this calculus stuff, and let's see how we do here. So let's start by talking about tangents and the derivative at a point. So recall that the average rate of change, excuse me, at a point is defined as follows. And so this is something we did even, kind of looking back at pre-calculus here. You should have done something like this. So the average rate of change of y equals f of x with respect to x over the interval x1 to x2 is simply that. It's just the slope, which is change in y over change in x. That's what that delta means. Don't forget this is change in y over change in x, right? That's what that is. And anytime you see that change in, it means 2 minus 1 or final minus initial, like that. And so that's what we do on the top. That's what we do on the bottom, 2 minus 1. Essentially, this is y2 and y1, okay? And you do the difference between those. And what we're doing, instead of just doing those 2 points, is we're picking one point on our curve, right? We're picking this point, and then we're moving a distance h to the right. So we're starting with x0 and moving to x plus h. So what that does is it makes the first point x and the second point x plus h. And so what happens in a little intermediate step in the denominator is you get x naught minus x naught plus h, like that. Oops, I'm sorry, I wrote that backwards. You get x naught plus h minus x naught, like that. And then the x naughts cancel, and you're left with a positive h right there. Okay, that's where we get that h. And then over here, it's just going to be left as really down there. It's x naught instead of just x1, so I'll put the zeros there. So it's x0 plus h minus f of x0, so something like that. And then that's your formula. You can use that to calculate your average rate of change between the 2 points. So in other words, it would be between this point right here, this point right here. We're essentially drawing a straight line right in between them, as you see there, and then taking the slope of that straight line. Assuming that our curve in between is smooth and continuous, then that slope of that line would actually be the average slope of all the points in between. If you could somehow go in and draw in every possible tangent line to this curve in between there, and then take the average of all of those tangent lines, it would become the value of that slope of that line between the 2 points. Okay? So a very important idea to remember there. So here, how about slope of a curve at a single point? Well, now we have this idea that we can start to use. And so I'm going to go back to the previous page. I want you to take a look here first, though. We've got this here, and we've got the same thing down, except this time we've added this limit right there where h goes to 0. So if I come back to this page, clean it up just a little bit, what we're doing is saying, all right, we want to figure out what the slope is of the tangent line at that point. That's this red line right there. We want to know, what is the slope of that point? Well, if we just pick this first point and we pick this second point and we do the slope between them, we'll get something that might be kind of close. Here, it's not very close. This slope's way down here. This slope's way up here. They're not very close. So how could I make this better? Well, what if instead of picking this point that's way far away, what if I make h smaller, like half of what it is? So instead I use h right here, and I look between these 2 points. When I do that, and I draw in the tangent line, it's a little closer to the slope of this other one, right? I've moved closer to the slope of the actual red line there. Let me show you the red line. Okay? I've gotten closer to it. And so then you say, well, how can I do that even better? Well, why don't we cut h in half again? Let's do h right here. If I do h right there, I'll do this one in blue or something, and I draw in this tangent line right here, right? Then what do I end up with? I end up with something that's now even closer to that red line, to that slope. And so how do I make that even better? And hopefully you're thinking, well, I just move h even closer, right? So and essentially, as we move h closer, we're just making h smaller and smaller. It's we're taking smaller and smaller steps away from our original starting point. And when I do that, I have this new line, and I'm going to get a tangent line that's more like that. And I'm getting even closer. And if I just keep moving this h closer and closer, making h smaller and smaller and smaller, I'm eventually, like, let's pretend we could look and zoom in right here on that point, right? Let's say we could zoom in like this. Here it is, we're zooming in. What we're essentially doing is ultimately getting so far down that we're looking at, here's the point we were originally looking at, and we're looking at the point that's right next to it. Like, pretend we could go down and get down to that point that is exactly next to it. Maybe I'll move it a little closer. You know, like here are all our points that make up the line, like this, the curve. And what we're doing is we're looking at this point. This was our original point we're looking at, and we've gotten down to where we've pushed h basically down to 0, where there's practically no distance between them, and we're drawing in a tangent line between those 2 points, right? And getting the slope between those 2 points. And it's, for all practical purposes, for everything you can do, that is going to be the slope at that point, because we've essentially taken the limit that we've gone down to basically just 1 point, because these points are infinitely small and they're infinitely close together, and so that's what we're going to have there. And so that's why we're doing this limit right here. We're taking this limit as h goes to 0, so we can push these points, that h, really close, and push our 2 points that we're looking at really close together. And for practical purposes, it's like we're taking the slope at that single point, okay? And so this would be a nice way to do it. So let's take a look at this first question. It says, find the slope of the curve y equals 1 over x at any point x equals a, does not equal 0. What is the slope at x equals -1? All right, so we can see over here to the right, this is the actual graph of 1 over x, y equals 1 over x. And so what we're interested in is finding the slope at a single point, in particular, the point x equals -1. Right, so somewhere over here. So it's like we're trying to find the slope of this line right there, okay, that comes along and is tangent to the curve at that point. It means it comes along and just kind of skips off it and just touches it at that one little point. So let's do this. So A. So what we can do is actually use our above formula and do this. So m is a function of x. Our slope is a function of x. We're going to have the limit as h goes to 0, and then we're going to have f of x plus h. So that's our function with x plus h plugged in for x. So that'll be 1 over x plus h, okay? And then we have to do minus f of x, which is just 1 over x, and all divided by h, okay? Now we just need to start doing a little bit of algebra, because if we try to plug in, ultimately our goal for taking limits is typically to get it where we can plug in whatever we're taking the limit as we approach without getting some sort of bad result like dividing by 0. So let's take a look here. If we try to plug in h right now, we'll end up dividing by 0 right there with that h. So we need to do some algebra first. So let's start off by bringing that 1 over h out front. So limit as h goes to 0, and I'm going to bring this h in the denominator out front, so it's a 1 over h. Dividing by h is the same thing as multiplying by 1 over h, times, and I'm going to make this 1 over x plus h, and then minus 1 over x. Now I cannot subtract those two until they have the same denominator, so common denominator between the two of them would just be x times x plus h, so x times x plus h. That's the common denominator between the two of them. So to get this one on the left, I'd multiply it by x over x. To get this one on the right, I'm going to multiply it by x plus h over x plus h. Okay, like that. And that'll give me this common denominator right there, x times x plus h, in the denominators for both of them. All right. So my next line, limit as h goes to 0 of 1 over h times, and now here we have x plus h, x times x plus h, like that, in the denominator. And then we've got in the numerator, this is going to just be x, and this is going to be minus x plus h. So it's x minus x plus h, just like that. Then we can go ahead and distribute that negative sign through and actually do the subtraction here in the numerator. And we'll get limit as h goes to 0, 1 over h, times, this is x minus x, so those are going to cancel, and then this minus is going to apply to h, and we'll have a negative h over, and then the denominator I'm going to distribute, or actually I'm just going to leave it. It's going to be x times x plus h, just like that. Now I have a 1 over h here, and I have an h up here, a negative h. So I can actually go ahead and cancel out the h's and just leave me with that negative. And I'll have limit as h goes to 0 of negative 1 over x times x plus h. And at this point, if I plug in 0 for h, I'm not going to get an error. It's going to work. And so I can go ahead and do that. That h will go to 0. And zoom in here a little bit. And this will be equal to, so I'm going to actually go ahead and take the limit. This will be negative 1 over x times x, which is x squared. All right, and so this will be our slope as a function of x. In other words, what we've done, without specifying a particular point, we've just done it for any general point x. By doing this, what we've done is come up with a function that allows us to plug in any value of x we want and figure out what the slope is at that point, okay? And so we could do something like right here where it says we want it at any point x equals a, all right? So we can do that at any point x equals a. That means I could just plug this in, make it m of a is equal to negative 1 over a squared. So at point a, whatever it happens to be, I plug in some value for a, and there you go, you have it. But it also specifically asks us for the point x equals negative 1, which means I just simply do, get that out of the way, we do m of negative 1, which is negative 1 over, and then we put in negative 1 squared. So negative 1 squared is 1, and it's negative 1 over 1, so this is just negative 1. And that would be the slope of this red line right here. Okay, this one right over here that I drew in would have a slope of negative 1. Okay, so there you go. That's how we were able to do it and to find the slope at a point. So then let's take a look here. And the next part asks us, where does the slope equal negative 1/4? Remember, our equation m of x was negative 1 over x squared, like that. And so for part B, it says, when do we get that slope? So what we can do is actually plug in negative 1/4 for the slope equals negative 1 over x squared. Okay? And the negatives will cancel. And so we have 1/4 equals 1 over x squared, which means 4 equals x squared. Take the reciprocal of both sides. And then we've got x equals plus or minus the square root of 4, which is plus or minus 2. Okay? And so if we take a look here, we can see at both places, here is the point, here's negative 2, and we come down, and our slope right here, you see that line right there, is going to have a slope of negative 1/4. And if we go over here to x equals 2, we have that same slope. Notice those two lines, other than the way I drew them, are actually very parallel. Okay? And so there, that's how we were to do it. So part C, what happens to the tangent to the curve at the point A, comma, 1 over a as a changes? So if you take a look at this, you could write this out in words. We're basically saying, if I look at this point, I have a negative slope, right? And as a changes, as we move toward a positive a, as we go this way with it, right? My slope, which was very negative, becomes less and less negative, and it eventually, over on this side, will start to become closer and closer. As this becomes more and more horizontal of a graph, it starts very negative and it approaches 0. On the other side, if we start way over here, okay, and I'll do this in a different color so it's a little more easy, is we'll have this slope, And then as we move along, we get to that slope and then to this slope. So we started with a slope that was very close to zero, especially if we're way out here. It's very close to being horizontal and very close to being zero. And as we move along, it's going to rotate. Our slope is going to rotate around like this, and it's going to become more and more negative. So on the negative side of the graph, our slopes become more negative, starting at zero. And on the positive side, as we move toward the right, we start off at a very negative slope, very steep and vertical, and move toward a zero slope. Okay, rates of change, derivative of a point. So let's take a look here. The expression f of x plus h minus f of x over h, where h does not equal 0, is called the difference quotient of f at x naught with increment h. When we apply a limit as h approaches 0 to the difference quotient, then that limit is called a rate of change. Okay, so let's look at our definition here. The derivative of a function f at a point x naught, denoted by f prime of x naught, is f prime of x naught equals the limit as h goes to 0 of f of x naught plus h minus f of x over h. So that's what you usually will call this. It's denoted that, but it's called, a lot of times it's called f prime of x naught. That's what this here, that's how you would say it. And so provided that limit exists, that's going to be what is called our derivative. All right, and so this is called our derivative. Okay, and it's the derivative at that point. So note that the notation f of x prime is what I just wrote up here. It's read f prime of x, or x naught in this case, but f prime of x naught, whatever's in there. So what do these 5 phrases have in common? Slope of the graph at a point, slope of the tangent to the curve at a point, rate of change at a point, derivative of a function at a point, limit of the difference quotient at a point. And basically what they all have in common is they're essentially telling you the same thing. The slope at a point is the slope of the line tangent to the curve. It is also the rate of change at a point. It's how quickly the point is changing as you move from point to point. We also call that a derivative of a function, which we just talked about there, something called f prime. And it's also, as we saw on the previous page, it's the limit of the difference quotient, which actually we see right here. It's the limit of that difference quotient. Okay? So basically, when you're told that, you're essentially looking at the same thing every time. Okay? So that brings us to the end for this section. You're going to get 2 days on this section, even though it's not a super long video, but go back, take your time, rewatch it a few times, think your way through it. Getting this idea down right now of slopes of tangents to curves and stuff is very, very important. It's something we're going to lean very, very heavily on for the rest of this calculus and into calculus 2 and 3 if you take that. So really take your time, spend some time just thinking it over, really just making it make sense in your head until you understand this stuff, because a lot of this is very intuitive and has a lot to do with just kind of your intuition about things and your understanding about things, more so than the math you're doing. Doing the math is very important, doing the algebra and knowing the steps, yes, but what is also equally important, maybe slightly more important, is understanding this idea here. Okay? So other than that, that's it, and I'll see you in the next video.